Think for a second about everything you've already done on your device today. You probably streamed something, maybe ordered some groceries, or fired off a dozen messages on a work channel. And we all just kind of expect our digital lives to work flawlessly, right? Instantly, with zero interruptions. But behind that perfectly smooth, frictionless experience is this hidden, incredibly high-stakes world operating at literally blinding speeds. So today, in this explainer, we are stepping right into the shoes of the people who actually keep the internet running. We're talking about cloud engineers. We're going to follow one engineer through a single, super fast-paced day just to see exactly what it takes to keep our digital universe from completely collapsing under its own weight. It's a story about the invisible architecture powering modern life and the relentless problem-solving it takes to keep it completely invisible to you.
Okay, so let's set the scene. It's a peaceful morning. The sun is coming up, offices are waking up, and the clock strikes 9:03 a.m. Right at this exact second, a truly breathtaking amount of data is moving across the globe. You've got millions of people shopping online, thousands streaming movies in 4K, banks are processing these massive, complex volumes of financial transactions, and ride-sharing apps are calculating millions of geospatial coordinates every single second. And honestly, everything seems perfectly normal. The digital ecosystem is just humming along beautifully. Servers are silently crunching petabytes of information while the rest of the world is just finishing their morning commute.
But let me ask you something, and I really want you to put yourself in the mindset of an engineer for a minute here. What actually happens when a core server suddenly blinks red? Like when a localized failure in a massive microservice architecture threatens to just cascade and take down an entire platform. How does the internet not just totally break when a critical node goes offline? Because let me tell you, these highly distributed, insanely complex systems, they for sure do not fix themselves by magic. They require constant vigilance, brilliant architecture, and someone at the helm who knows exactly how to navigate a digital storm.
So our day actually begins before a single line of code is written or any new feature is shipped. Coffee in hand, our cloud engineer opens up their primary monitoring dashboards. They're scanning telemetry across thousands of global instances, checking the baseline metrics to make sure everything is operating right within those highly specific thresholds. And what they're looking for is total stability across the entire cluster. You want optimal compute resources, steady memory allocation, low network latency, and database queries functioning perfectly with zero deadlocks. It is the absolute ideal start to a shift. Just a brief moment of calm where the infrastructure is behaving exactly as designed.
And then bam, the PagerDuty alert goes off. Suddenly, the health dashboard lights up with critical warnings. Compute resources on the primary application service have just spiked to a terrifying 99% utilization. Latency is absolutely skyrocketing, API response times are dragging into the seconds, and automated customer support tickets are already starting to flood the queue. The system is under immense, totally unpredictable pressure. And here's the thing, if this bottleneck isn't resolved in minutes, the entire platform is going to time out. We're talking a complete service outage. The clock is officially ticking and the adrenaline kicks in.
Now, good cloud engineers don't panic, and they definitely don't guess. They triage. By diving straight into the metric logs and evaluating the incoming request headers, our engineer quickly isolates the anomaly. And guess what? It's not a memory leak from a recent code push, and it's not a database lock. The network traffic is just surging exponentially. Turns out, a marketing campaign unexpectedly went viral on social media, and it is hitting the infrastructure with 10 times the provision capacity. Thousands of new users are flooding the application every single second, just completely overwhelming the current compute limits.
So instead of stressing about a crashing platform, our engineer calmly initiates an automated response protocol. With just a few programmatic commands, capacity begins to dynamically multiply. It's awesome to watch. One instance rapidly scales to 2. 2 replicate into 5. 5 become 20. In literally a matter of seconds, the infrastructure expands horizontally. The load balancers instantly recognize these new instances and immediately start distributing that massive wave of incoming requests across the newly provisioned fleet. API response times drop right back to normal baseline levels. And those thousands of new shoppers who were aggressively hitting refresh, they didn't notice a single stutter.
And honestly, this concept is the true power of cloud elasticity. Auto-scaling ensures that instead of over-provisioning super expensive, static hardware that just sits idle most of the day, the architecture dynamically spins up ephemeral compute instances exactly when the load demands it. And maybe just as importantly, it spins them right back down when the surge passes, which totally optimizes costs. It's a brilliant architectural paradigm shift. Actually, scratch that, it's an absolute game changer. It keeps modern apps highly resilient under crushing demand without companies needing to maintain massive warehouses full of dormant servers.
All right. Phew. Crisis averted. The engineer finally goes for that first real sip of coffee, taking a well-deserved moment to breathe. But
Before the mug even touches their lips, an automated deployment notification pings in the team channel. Yep, the dev team has just merged a massive new feature branch into the main repository, and the release window opens in exactly 10 minutes. Because in modern cloud engineering, the environment is never static. There is no downtime to just chill. There is only continuous integration and the relentless forward momentum of shipping new code to users. So this is where a robust CI/CD pipeline takes over, essentially functioning as the central nervous system of software delivery. The new code is automatically pulled down, instantly run through a really rigorous gauntlet of automated unit and integration tests, and subjected to deep vulnerability scanning just to catch any exposed secrets. Once it's validated, it's pushed seamlessly into production using a canary deployment strategy. Think about that for a second. What used to require entire weekends of painful, highly coordinated planned downtime, that now happens continuously. Complex new features roll out to millions of active users in mere minutes, with absolutely zero downtime. But hey, keeping the environment stable and continuously updated, that's really only half the battle. The other half is keeping it intensely secure. Right on cue, another alert flags a severe anomaly. Except this time, it's not organic viral traffic. It's a massive, coordinated brute force attack originating from a global botnet. But the automated defenses are already stepping up. Between active threat monitoring, strict zero-trust identity access protocols, and dynamic web application firewalls, those malicious requests are instantly black-holed at the edge. The encryption protocols are holding strong. The cloud engineer is basically operating as this invisible, highly automated security perimeter, totally neutralizing threats before they ever even touch the internal network. Let's fast forward a bit to the afternoon. The immediate fires are put out and our engineer is now sitting in a critical architecture planning meeting, and the product lead drops a pretty massive bombshell on the room. They say, we're expecting 5 million active users for a major product launch next month. Yeah, the room goes totally quiet. Everyone at that table knows exactly what's at stake. Because if the underlying infrastructure isn't meticulously architected for that specific kind of concurrent throughput, the entire platform is going to buckle under the weight, resulting in a highly public, disastrous launch.
But our cloud engineer? They don't sweat it. They just step right up to the whiteboard to map out a highly available, fault-tolerant architecture. They designed this beautifully decoupled system using aggressive load balancing, read replica databases to handle all that query volume, heavy caching layers to reduce the backend strain, and a really robust global CDN to drastically slash latency at the edge. And just like that, the anxiety in the room dissipates into focused action. You see, a huge part of cloud engineering isn't just reacting to incidents on the fly, it's proactively architecting scalable systems so those critical incidents never even ignite in the first place.
Yet, despite all that brilliant planning and redundant architecture, true worst-case scenarios absolutely still happen in the physical world. Literally out of nowhere, a massive physical data center experiences a total, catastrophic power failure. Entire racks of hardware, petabytes of active data, thousands of virtual machines, they just vanish from the network in a single microsecond. By all traditional metrics, this should be a catastrophic, headline-making event, right? But on the user end, people are still swiping, still streaming, still checking out. The user interface doesn't even stutter. So how in the world does a major physical outage result in absolute zero downtime for the end user? It really comes down to the brilliance of automated cross-region failovers. Modern cloud environments are literally never tethered to a single point of physical failure. The exact microsecond the data center went dark, automated health checks failed, and the DNS routing protocol seamlessly redirected all the live traffic to a completely redundant availability zone hundreds of miles away. It is complete, 100% disaster recovery, executed flawlessly in milliseconds, completely without human intervention. Wild, right? Finally, the clock hits 6 p.m. Our engineer runs one last comprehensive health check across all the global clusters, and the monitoring dashboards are back to being a beautiful sea of green. Compute, memory, networking, databases, everything is fully stabilized. The auto-scaling groups have spun down the excess capacity, and the threat metrics are completely quiet. They close their laptop, pack up, and head out for the evening. There are going to be no frantic tech headlines today, no trending hashtags on social media complaining about a massive global outage, just total, reliable silence. Because at the end of the day, behind almost every single application we rely on, whether that's global video streaming platforms, real-time financial markets processing billions of dollars, or even just the remote enterprise networks keeping global businesses running, there is an incredibly complex, globally distributed infrastructure. And standing between that fragile infrastructure and total utter chaos are these unseen digital problem solvers. They're the ones constantly monitoring, scaling, securing, and architecting the systems to ensure our highly connected world literally never skips a beat. Which really leaves us with one final thought for you to consider. After seeing the relentless pace, the massive global scale, and the invisible, high-stakes problem-solving required to keep the modern world spinning, is this a challenge you'd actually want to take on? Are you ready to architect the digital future and build the systems that millions of people rely on every single day? Something to think about. Thank you so much for joining me to break this all down, and I will catch you on the next explainer.